All right, today's video is part 2 of gravimetric analysis. So if you haven't watched the first gravimetric analysis video, make sure you do that first. Otherwise, this one's not going to make a whole lot of sense. So, without further ado, I'm Jason Neal, and welcome to The Bald Chemistry Teacher. Okay, today we're going to talk about a mistake that is commonly made in gravimetric analysis, but before I do, I want to talk to you about swimming. Yep, that's right, swimming. Now there's a big difference between swimming in a swimming pool or a freshwater lake or stream versus the ocean. When you swim in the ocean, if you've ever done it, and you get out and you just lay in the sun and let the water dry, let it evaporate off of you, you might notice a white crystal substance that forms on you. That is the salt. Because when salt water evaporates, the water goes into the air, but the salt stays behind on your skin. Okay? Similarly, if you were to spill some soda pop on the counter, and if you just wipe it up with a napkin, if it's sugar soda, that sugar stays behind after the liquid dries or evaporates, and the counter is then sticky afterwards. When you sweat, the liquid evaporates, and sometimes, when I've worked really hard, I have salt crystals left behind on my head or on my arms or something. So, that's an important principle, and it's going to relate to gravimetric analysis because when a liquid evaporates, whatever is dissolved in that liquid stays behind. So now, let's look at the gravimetric analysis example from last time. I had a yellow filter paper. Well, the filter paper was white, but it was covered with a yellow precipitate. And I poured that liquid through the filter, and it trapped that yellow solid, the yellow precipitate. Now, I made a big deal about taking a squirt bottle and rinsing or washing the precipitate. You need to add extra water to the precipitate even after everything has gone through. The reason for that is you want to wash off any dissolved ions. You want to get every single ion to go through that filter. If you don't, okay, the ions that are present when you're pouring that liquid through, yes, the lead chloride or the lead iodide stays in the filter. But there's also some extra lead ions, some potassium ions, some nitrate ions. Those ions are there in the water. And if you don't rinse them through the filter, then the liquid will evaporate and those ions, those extra dissolved ions, will stay in the precipitate. Kind of like how salt water, when it evaporates, the salt is left behind. So you want to make sure there's nothing in that filter paper except water and the lead iodide. All the other ions need to rinse through, so rinse it with extra water. Now, what happens if you fail to do that? Well, in the last video, I took out that filter paper covered with yellow lead iodide and I put it on the scale and it weighed 2.44 grams. Now, out of that 2.44 grams, 0.74 was the filter paper. So if you remember, I subtracted those, the 2.44 minus the 0.74, and I got 1.70 grams of lead iodide. Now, what I needed to do is I needed to change that 1.70 grams into moles. So I took 1.70 grams and divided by the 461 grams per mole, right? And I got 0.00369 moles. And that was my moles, 0.00369 moles of lead iodide. Now, because of the 2 in the formula for PbI2, the 0.00369, if you double those moles, that will give you the moles of the iodide. So the moles of iodide was 0.00738. That's 2 times 0.00369, okay? So 0.00738 moles of iodide, that was the moles of of iodide, and that equals the moles of potassium iodide. Okay? I then could simply take those moles and divide by the liters, 0.00945, and I get my molarity, 0.781. But what if I failed to rinse the precipitate? What kind of error is that going to give me in my results? Is my 0.781 molarity accurate? No, it's not. Okay? And the reason for that is because that 1.70 grams of lead iodide is not 100% lead iodide. So that 1.70 grams is too much. That includes some potassium ions, some nitrate ions, some lead, some extra lead ions. So that 1.70 grams is artificially too big. The actual mass of just the lead iodide is going to be somewhat less than 1.70. How much less? We don't know. I don't know how much of the ions stuck to that yellow precipitate. So if 1.70 is too big, so is 0.00369, right? Make sure you pay attention to the math. If 1.70 is too big, so is 0.00369 moles. And if that's too big, 0.00738 is too large of a number. It's artificially too large because it's not the moles of iodide. It includes other ions too. Therefore, the numerator, when I calculated my molarity, my numerator was 0.00738. That numerator is too big, and therefore, my final answer, my molarity of 0.781, is too large. So, if you fail to rinse the precipitate, the molarity that you end up with is going to be artificially too big. So make sure you understand why that is. You can kind of follow it. When you make a mistake in a lab, follow the math. If 1.70 grams is too big, so is the numerator of my molarity, and therefore my molarity is too big. All right, that is probably the most common mistake made in gravimetric analysis, and so I wanted you to understand the mathematics and how that failure to rinse the precipitate goes all the way through the calculations and ends up with a molarity that is artificially too large. Well, thanks for watching. If you find these videos helpful, make sure you like and subscribe, and I'll see you next time on The Bald Chemistry Teacher.